everyone for joining us on another monthly ECSS Symposium. This month we have Sudhakar Panlaikantam from NCSA talking to us on a project called Atomistic Characterization of Stable and Metastable Alumina Surfaces. We have one of the co-PIs on the call also, Sean Coleman from University of Arkansas. Thank you for joining us. And there are a number of components to this ECSS project, from looking at parallel scalability of a component of the LAMPS community code on Stampede, data transfer between Stampede and Gordon, and also integration into the GridChem Science Gateway. So a lot of different and interesting aspects here. I want to thank Sudhakar for preparing a talk for us. And with that, why don't you go ahead and get started, Sudhakar?
Okay. Thanks, Nancy, and thanks for this opportunity. So let me get started, see if I can move this presentation. Okay, it's not moving. Oh, I have to do next here. Okay, yeah, so this is essentially what Nancy was just saying. The PI is Doug Spirod from University of Arkansas, and Sean from University of Arkansas is here on the call, so he may answer some questions that I don't know too much about. The grant name, and so from the Exceed side, I was kind of nominally leading this team who was working with Sean and Doug. So Yang Wang should be, I think there's a typo here. Sorry about that. He's actually in China on vacation, so he is not going to be able to answer some questions that we have. And Mark is in the audience, and he will be able to answer some questions pertaining to visualization if I don't explain it correctly. Okay, so we'll do next. So, I mean, here's just a quick introduction to metastable alumina. So this is actually, picked from a paper that it looks like it's getting cut off here due to some resolution things. This is a Journal of American Ceramic Society paper, I believe in 2011 or something. Anyway, so what it shows is that this alumina is a material that is broadly used for various kinds of purposes in industry, absorbents, catalyst carriers, coatings, soft abrasives, and I know that it is also a material that is used in electronics industry for one of these, substratum, a substratum on which other layers are laid out. And so this, this graph describes various ways of making various kinds of alumina. I mean, you can see that this alpha, Al2O3, which is a stable form, but there are various kinds of other forms like chi and kappa, kappa prime, gamma, and so on and so forth. I mean, this talks about this gamma form, particularly, it's called a transition aluminum, which is important in many areas. And there are various kinds of transitions, and it is useful to understand the characteristics of these kinds of alumina, and then maybe, modulate those things for various properties. Okay. And this is just a general description of how some kind of a characterization is done. I mean, there are, of course, X-rays, which are a kind of radiation that comes out of some metal plates when electrons are impinged on them. And then there is the materials here of various kinds with different kinds of lattices. And so this radiation is dispersed by the atomic centers in molecules, or in metallic and metal oxide systems. And so there is so once the diffraction occurs, the radiation goes in some kind of angle away from the center, and it is captured basically on what is called an evolved sphere, and a diffraction pattern is obtained, which is a representative of the actual structure of how, these atoms are oriented in a lattice. So this leads to what we call molecular and solid state structure of materials. So both are important, and that's what is called characterization. And eventually we want to see if we can actually engineer a crystal for a particular function. And of course, the function is what is observed in implements that contain these materials. The general introduction for these materials, and so this is actually a slide that Sean provided us early on, just to describe what the diffraction pattern is. There is this evolved sphere. So the diffraction occurs, on a much larger volume, but the pattern on a sphere, which is described by 1 over lambda, is what is actually used for representation of the lattice. And so there is this intermediate reciprocal space that is used typically in these experiments, and so there is a correlation between this reciprocal space and the real space. So there is usually a Fourier transform that brings back the real 3D coordinate space once from the reciprocal space. So that is exactly what is shown in this. So this X-ray diffraction, so what I showed before is experimental setup, how experimentally a diffraction pattern is obtained, but the same thing can be computed. And so LAMMPS is a community code that is widely used in many centers, including XSEED systems. The X-ray diffraction compute, which is a plugin in LAMPS, is very generic. As it says, it is not only for X-ray radiation, but also some electron diffraction can also be computed using this XRD compute plugin in LAMPS. So it is of course integrated into LAMPS, and there are two ways of using this. One is to do a static snapshot diffraction pattern for a single image, or you can do a time averaged one through just an MD simulation of each snapshot and then averaging over time. And in reality, so there is a time involved, and this so this time averaging is what would be comparable with experiment if the right quantities are compared. And so the visualization procedure creates this diffraction pattern composed from the simulations based on intensities computed. So some math is coming in just a minute to show this is all computable. So this is just to describe very briefly the X-ray diffraction algorithm. A 3D mesh of points filling a volume of reciprocal spaces created from the entire domain of the atomic simulation cell. And so the mesh of reciprocal lattice points is built on a rectilinear grid. So the mesh, and each reciprocal lattice axis is associated with a vector corresponding to various edges of the simulation cell. And this lattice vector, the reciprocal lattice vector is associated with this reciprocal lattice point, and the deviation between the diffracted and incident wave are represented by these values kd and ki, which are used in this expression for k for the lattice vector. And so this is the standard Bragg's law, and I think so this is the kb, which is an average value. And So the diffraction depends on what are called structure factors, which are again dependent on what are called atomic scattering factors that come from each atom. So each atom contributes to the structure factor and the diffraction pattern, as can be seen. And in this computation, the computation is reduced by restricting the number of points considered, using this kind of a cutoff approach. And so Yang was looking at how to parallelize this code. So this code is already parallel in some respects, but he was looking at how to parallelize it further. Let me see if I have some initial graph here. So for example, this graph was provided by Sean and Doug when we started considering this project. So what this shows is that the code, the LAMPS DS, DS represents Doug's PROD, the PI, is already scaling, up to 250 processes or so, and then after that it was, I think, tailing off. The efficiency is, becoming less and less. And the other issue that we were looking at is the memory per core, which is kind of increasing in a nonlinear fashion, which was also an issue. So we wanted to reduce the memory, per core, and as well as to make this code scale further beyond this 250. So go back. So that's what we were tasked to do, and Yang from PSC looked at this, with Doug during some interactions, and so they initially looked at how it is parallelized. So it looks like it is atom centered, and as we have seen, there are multiple layers in which the parallelization can occur. So one is through this grid, what's called a K-space mesh, and so after looking at how this is organized, Yang essentially separated the XRD component and made a standalone piece of code and parallelized it trivially by just parallelizing through this K-mesh initially. And that simple parallelization shows some improvement in performance. We don't have numbers yet here. He has actually submitted that code for Sean to look at. So this code has not been implemented in the Science Gateway yet, but this is still work in progress. And so further improvement in the parallelization would come from going beyond that simple K-mesh loop inclusion, but also to go over all the atoms and either using MPI or OpenMP, depending on where the code would run. So we are trying to test this in multiple platforms. Yang is testing this on the SMP at Pittsburgh, the black light, and there is a version that is implemented on Gordon, which is a kind of a virtual, a shared memory kind of machine. So it has its own peculiarities, which is not a straightforward SMP like blacklight. And eventually we want to also move to Stampede, which is a totally different kind of architecture with distributed memory and potentially using the mics in that system. So all those things are still need to be done. So the preliminary work is being done on blacklight, and there is a version that is implemented on Gordon. But Yang has submitted the code when I just went for vacation, so we have to explore how the code is parallelizing on Gordon at this point. Okay, so this we have already seen this. This is the base from which we need to improve at this point. So we are going to have a couple of students help us implementing this. There is a summer project that has been initiated. Paulo Ramiro Bermudez, who is going to work on implementing some of the structures onto the microprocessors on Stampede. This work has just started, and we'll also be working with a campus champion fellow, Luis Guerra Parra, to implement an MPI version of this XRD compute for multi-core and many-core systems. So these projects are just starting at this point. So when Yang comes back from his vacation, I think we'll be going full steam on this. Okay. So this is some conditions that I took from this paper that Doug sent me. This contains some of the parameters. We have seen the parameters like what kind of radiation that is to be used, and what kind of potential that is used in the simulation. So this, as I was telling, there are various kinds of radiation that can be used based on what metal atom is actually dispersing the initial radiation and the corresponding energies, and this embedded atom potential that is used is essentially something like a reacts FF force field, developed by many people and published. And these are the cell parameters that are implemented in that paper. And maybe Sean can comment on some of these maybe later. And for the visualization, so we need to look at what are called diffraction intensities. So there is this Lorentz polarization factor that is part of this intensity computation, and these intensities are then plotted based on some kind of a visualization protocol where a particular axis, the zone axis, is chosen, and the visualization is dependent on what axis and how what the volume of the visualization is. And so one of the kind of criterion for choosing or restricting the amount of volume is to take the thickness of this the slice, the hemispherical slice, and the resolution of the reciprocal space mesh. And this is termed to be about between 1 to 5 reciprocal lattice points. And so that leads to some visualization. And so we need to implement all these things so that users can easily access this. And so we wanted to integrate the LAMPS code along with visualization into a science gateway. And okay, so I call it C-Grid Science Gateway at this point because we are doing things that are beyond chemistry. For example, Doug and Sean come from an mechanical engineering department, I believe, at University of Arkansas. So to make it inclusive, we are calling it science and engineering applications grade, instead of just a chemistry grade, as it was before. Though underneath a lot of chemistry computation is actually involved in this case. So the integration involves, of course, deploying the applications on remote resources, So the initial implementation is for Gordon at SDSE, and of course once this is deployed, it has to be registered in a registry. This registry includes various kinds of characteristics of the deployment, like what is the path and what kind of compiler used and so on and so forth, how to access the application, what kind of script is used, if any, and if a script is used, what kind of arguments, etc., are to be supplied and so on and so forth. So that is some kind of a bookkeeping for an application in the Science Gateway. And of course, we need to register the users to access this application. So we initially registered the ECSS team. Mark and Doug were made PIs, and Sean has joined. Sean, who is a graduate student who cannot be a PI, is now under I think Mark's PI-ship. He can also join Doug's PI-ship trivially. And so since this program, this compute is still not public, it is still experimental and it is still being tweaked, we need to restrict the access to this application to just this ECSS project team at this point. And we demonstrated this restriction to the PI, and Afon, who's in our team at NCSA, implemented this access restriction, and we demonstrated the restriction, and then of course we let now Doug to access this as an independent PI, but it is still restricted for others, so others don't have access to this on the GridCamp Science Gateway yet. So once this matures, then we'll probably release it to the public. So currently the workflow consists of a LAMP execution which may contain XRD as a compute, and parsing the resulting diffraction patterns into something usable, and then taking the derived data from this parsing into Visit, which is a visualization software that is deployed on Gordon. And we have already enabled the PI and co-PI to use this. We have tweaked the number of cores, processors, or nodes used on Gordon, and the amount of memory that can be accessed through modification of the scripts for the team. Okay, and just this to show that how it is accessed through the gateway. This is just an original computational chemistry gateway, now called CGrid. So here we have an application called LAMPS. So we had a standard LAMPS available on multiple resources already, the Blacklight, Truffles, Gordon, and Stampede, and we have already introduced this DS as a module. So we can introduce multiple modules for a given software suite, and then you can either restrict or open, make it open accessible based on the requirements. And so that's what is shown here. And of course, there is a way to add input information, multiple input files, and so on and so forth. Or you can add or edit some files on the fly if you need to, if they are simple enough. And so this one shows so one of these jobs that were submitted and completed. And you can see finished. I don't know whether you can see this under the status column. And so this is what we call a file browser implemented in the Science Gateway. A large number of files that result from such computation, and you can either look at one or the other outputs and determine how the computation completed or not. And eventually, you'll see that there is a visualization as an image, a PNG file that is dumped at the end of this visit run. which is all part of a single workflow at this point. And okay, so this is some work that is done by Mark here. Some of these scripts are of course provided by Sean and have been maybe modified or adjusted to run in Gordon under the Gateway organization. So there are these SCED outputs. You might have seen them in the previous outputs here. I don't know whether we see SC. I don't know. Okay, so some of them are converted into this XYZ file. Yeah, so there is this SCED file here, alpha 337500 initial 100. So those files are transformed into an XYZ format file to be fed into a visit protocol. So originally when we started, the visit was only running on Trussell's part of SDSC, and there was some issue to run it on the Gordon, and eventually we found out that this requires a particular version of visit that was required for the VSMP based nodes, and Amit Chaurasia helped us build this particular version of visit for this VSMP, and now the workflow kind of smoothly continues to run visit after it completes the XRD compute from LAMPS. And so Mark played with various kinds of versions of launching visit. I think now he settled with using a Python-based script to drive the visit execution. And so there are again, multiple ways of driving the visualization computation. So the one called sessionless, what we call sessionless, which assumes certain standard parameters and sets the parameters for driving the visualization computation. The other way to do it is to let the user provide a session file. This session file is something like a file that is saved by running the visit locally and then saving the history of the execution in a session. And that session can be reused for another experiment, for a new data, with the new data that is computed in the workflow. And so we have a way to discover if the user has supplied a session file or not. If the user hasn't given a session file, then we'll default to a sessionless computation. If a user gives a session file, then we'll take the session file and then use the session file again through this Python script. So that's why it says, otherwise the scene is rendered with some default values. Okay, and so here is just again the PNG file, which is again available in the file browser, can be downloaded, and then you can use a standard visualizer, like a photo viewer or an image viewer, to visualize it locally on the user's desktop. So this is slightly more interesting visualization that Mark was able to deliver by modifying some of these parameters by changing the sphere value or reducing the volume of data and so on and so forth, using various kinds of scalar threshold and clipping and modifying the color maps. And apparently he discovered some kind of bug in this is in visit, I guess, right? And is this now reported, I believe, and somebody probably is looking into it.
Listed as pending.
Oh, it's listed as pending. Okay. Anyway, so we are also debugging visit software during this project. Probably it is kind of a service for the community in that sense. So the next thing that we plan to do is to deploy the same workflow using Apache Airavata, using Xbaya workflow management systems. Particularly, this workflow will be needed if we want to use multiple resources. For example, we want to use the user's allocations on Stampede and then move the data to Gordon for visit visualization. Of course, we can implement the visit on Stampede as well, and then do a straightforward workflow. That's probably something that we may want to also try initially in the first part of this immediate phase. And so we want to also do this workflow with both sessionless and sessioned visualization. And the other thing that we were contemplating of trying is to actually let the user control the visit computation interactively through some kind of connecting to a visit server. That is, a visit server is already running on Gordon, maintained by Amit, and so we have to discover some kind of a link where the visit server starts, and then we can go back and link from a visit application running locally on a desktop, and then drive the visualization from the desktop with a very, very fine control. So this is probably will not happen immediately, but this is if time permits, if we have time at the end of this project period, we will try this one. So the other directions that we were looking at is to change the rendering techniques. The first part is this plugin to load SAED directly to visit, which is essentially saying that instead of writing the XYZ file, you can have a plugin to just read the original data from the XRD computation directly into visit. This is probably some kind of a trivial thing. That's why it is in parentheses. And this is all again computation visualization with different resources. Perhaps also dynamically choosing the resources. Whether it is Stampede or Gordon or Blacklight can be chosen dynamically depending on some kind of a metric where whichever will be done the earliest for the user. So for that we need to actually implement a way to do what are called queue and run prediction, queue wait time and runtime prediction. We have just started a project with Warren Smith from TAC about that in GridCamp, and if that is implemented, then we can use that in this process. So this is again, I think, some kind of examples of how these point sprites and volume rendering would look like once implemented. This is all coming from Mars. So that's where we are now, and so we'll be looking at implementing these workflows and other things, separate them from this linear single workflow to actually create specific workflows in Xbaya and so on and so forth, which are very specific software for just driving the workflow alone on multiple resources. So that's all I have, and I'll be glad to take some questions. And Mark is here in the audience, and Sean is available if you have some questions about the actual science part of the project or about the setup. And he may also have some comments from a user perspective from the ECSS support system. So let me stop here and then wait for questions.
Sudhakar, thanks very much for a very good presentation. This talk really had a lot of aspects to it. I congratulate you and the team for working with not only the student engagement students, but being paired with a Campus Champion Fellow for the coming year. So you're really going out of your way to be involved in the wider Exceed program. So thanks to you and the PI team very much for doing all of that. I thought this was fascinating as far as the multi-site workflow capabilities and also integrating Viz into gateways. I've not seen a lot of that done in the gateway projects that we typically tackle. Mark, I wonder if you'd mind saying a few words about how easy or hard it was. It sounds like you did uncover some things where Visit didn't work quite as expected when you had multiple windows open. I wonder if there were any other things that you ran into trying to incorporate Viz into an existing gateway?
Actually it wasn't too bad once I learned enough of the Visit API to figure out what was going on. But the first month or so, it was just, I was flailing kind of blindly because their Python API isn't very well documented. But we did try out a bunch of different approaches, from trying to hand roll some Python to using the session files, which I think has a lot of promise, because that'll let the users determine exactly what they want to do with the visualization, and then they're not tied to always having to have a Viz consultant tied to their project or something like that. Actually, once it got up and running, once we figured out that we needed the Open MPI version of the Visit build, and how to actually have Visit restore sessions from different sources and stuff like that, it was pretty smooth sailing.
Great, yeah, that's good to hear. I think that's really an area where especially some of the remote Viz facilities could really play a role that they haven't too strongly yet in the gateway area, so that would be great. Sudhakar, I don't know, was it Yifan who did some of the gateway program? I was curious about the multi-site workflow and kind of how smoothly that worked, and the data transfer and scheduling and all the rest of that.
Okay, so no, we haven't really implemented that multi-site thing yet, but we have experience from the ParamChem project, which uses multiple resources, and we know exactly how it's going to work, and it's just a matter of implementation. And if you look at the timelines for this project, that is scheduled by the end of July, so we still have to implement that.
Yeah, that was on the future work slide. Yep, sorry about that, but yep, sounds exciting. I know there's a lot of interest in how well that'll work across Exceed.
Right. Yeah.
Sean, since we have a co-PI on the call, I wonder if you could say a little bit about how the ECSS collaboration has worked from your perspective, sort of what new things it's allowed the project team to do, what directions it's taken you that you didn't anticipate.
Well, as a domain scientist, I haven't had a lot of CS type background or visualization background, and it's great to have experts in the field to be able to just talk to, and who have learned a lot about my individual project, so that it can be more of a one-on-one engaging type scenario.
Yeah, thanks. That's exactly what we imagine these ECSS collaborations do, to sort of give people enough time to really concentrate on a particular project and make some headway. So.
Yeah, I would say that we have been very lucky to have Sean, who's been very tightly engaged with us from the get-go, and starting with actually giving us the code to deploy it on Gordon from the community side and all the way to, running with session files, going back and forth, testing some of the implementation, and so on and so forth. So I think this interaction is very useful.
Yeah, definitely. That's how these things work the best. So that sounds very good. Did you decide sort of from the outset to also make this available through a gateway? Or was it something that was more envisioned as a command line for a small PI group, and then you saw the utility and decided to add it into the gateway, or was that the plan all along?
So initially, one of the criterions in the project is to move data, smoothly, and so I did a demo of the gateway project and the workflows to Doug and Sean initially, and I think at that point we agreed that we should implement this in a gateway so that the data movement is essentially automatic, and it becomes usable by the community much faster after deployment.
Would you see this as being in use in classes, Sean, or for just the wider engineering community?
I could see it being used as a wider engineering community. Yeah, at first I had no real intentions to putting it into a science gateway because I just really didn't even know what they were. So, this is a great opportunity to have this work be able to be used by a lot larger range of people on some of the the higher class machines that are out there.
Yeah. Do you have any idea what the demand for this might be?
I'm envisioning it's going to be great, but that's my kind of pie in the sky type thinking. But this technique is basically going to allow users to directly compare results that they get with simulations to experiments, which has not been done to a great extent yet.
So LAMPS itself is a very widely used program, a software for molecular dynamics and studying materials. And as we were discussing, once this becomes mature, the label DS may disappear, and then it may be actually integrated into the general LAMPS distribution, and that way it will be accessible for wherever LAMPS is used. Beyond Exceed and the Science Gateway.
Exactly, and we actually just got this our first publication on this accepted and released online last week, so it's still very, very new, and we're just really excited about all the progress so far.
Tremendous, very good to hear. Questions from anyone else on the call for Sudhakar, for Sean, for Mark?
Just speaking of publications, I don't know if you guys are aware of the new capability to actually add your publications to the, when you log into the user portal, that you can actually, to put in the reference to publications, which we think is a good way both for you guys and then for Exceed to track and ECSS to track your publications. So if you're not aware of it, I think that would be great to, enter these latest publications that you've derived. Use that facility to enter that.
So that I think I referred to that publication during this presentation. It is in one of those slides. But I would also request Sean to go ahead and add it to that list in the through the portal.
I will.
Great.
Yeah.
I think. Sorry, go ahead. Whoever that was.
No, sorry, Nancy. This is Suresh. Hi, Sudhakar. One quick question on the gateways. So you're trying to set up a new community account and then trying to create a new instance of the CGrid for this project, or you're trying to funnel everything to the current CGrid and GridChem allocation?
No, it is going through the current GridChem at this point. But Sean and Doug can actually use their own allocation and then use this facility. They don't have to go through this community allocation, though right now they are using the community allocation.
I see. Yeah, it'll be great, like, when project like this, like, even though you're using Seagrid infrastructure, it'll be useful to register, like, it as a gateway and then request a new community account and then, like, get these jobs then through, so that will be useful during metric gathering and so forth.
Yeah, potentially if there is a huge, LAMS DS community, then I think that would be appropriate. But, we can cross that bridge when we get there.
Sure. Yeah. Thanks for that.
Sounds good. Any more questions for the group? Sudhakar, thanks very much. Very fascinating talk today. Thanks for everyone who's joined. We will not have a symposium next month. I hope to see many of you at the Exceed conference. And so the next symposium will be in August.
Thank you.
Thanks very much.
Okay.
Bye.